Hello, everybody. Familiar faces. I don't have my glasses, so I see Peter, Becca, but I don't see all of you. We'll be able to interact later on. I first want to thank the Fields MathEd Forum for inviting me. It's usual to thank the organizers, but when you like people and you get invited, it's a warmer invitation. So I'm really humbled and happy about that invitation to be with all of you. And I'm, yeah, this will create problems. Let's do this. And I want to thank the Fields Institute because I've been here for the last 2 weeks as a visiting scholar. Very interesting experience being in the building for 2 weeks and being in Toronto. So this is closing the thing today, but still it was a great experience. I wanted to talk about, when I got the invitation as a plenary, I wanted to talk about the work we do in our lab. I've been talking about that sort of work for the last year and a half, getting the chance to interact with different research groups all over the globe somehow, because I was in sabbatical. That's sometimes we do that. And I got a lot of feedback on the work we were doing. So I thought I'd take that opportunity to talk about the things we do in our research lab as a general thing, the general orientation, how all the profs that are working in our lab, which I could enumerate, and all the students, the sort of mindset we have and the things we work, and then go into a specific aspect of the work we do in our lab, which is linked to my research program, and go in more detail and some examples of. So if I've interacted with you in the past, you might have heard of these things. I see it as a great opportunity for going deeper if you have questions and interactions on this. Let's do this. I'll start, as I start most of the time when I talk about their work, with 2 quotes. A first one about Stephen Brown. I'm going to read it instead of being idle, because I think, and so you'll endure my English on this. So Stephen Brown says, so those are quotes that are very inspiring to us in our lab. So Brown says, and it's in 81. So one incident with one child, seen in all its richness, frequently has more to convey to us than 1,000 replications of an experiment conducted with hundreds of children. Our preoccupation with replicability and generalizability frequently dulls our senses to what we may see in the unique, unanticipated event that has never occurred before and may never happen again. That event can, however, act as a peephole through which we get a better glimpse at a world that surrounds us, but that we may never have seen in quite that way before. That's the first quote that is very inspiring for us in our lab. Every student has to read it and get a sense of it. And there's another one from Les Steffi, very influential also in the work we do. And Steffi says the following: since the 1900s, the mathematics of the curriculum has always been first the knowledge of mathematics of the curriculum developers. Mathematics was taken as a given, that's out there, that's real. We understand what mathematics is, apparently we do, but it has always been taken as the curriculum content that children have to learn. It is mathematics as known by adult people. This is what children had to learn. Children mathematics is mathematics, because Steffi was working on a concept called children mathematics. So children mathematics is mathematics because you look for a rational system that would explain that mathematics. And if you can formulate rational systems that are mathematical-like, then this constitutes legitimate mathematics. It's internally consistent and not contradictory. Now, people say kids make error all the time. Well, that's because you don't understand where they're at and you don't understand the internal workings of those kids well enough. That's Steffi saying. I don't have the stature to say these things. But why I start with these 2 quotes is because they are, as I said, influencing, but also it says what is our interest. Our general interest in our research lab is about the mathematics that people are doing. We're not about trying to find solutions to how to teach better or how to make sure that progressions of kids go well. We are, of course, compelled that things go better in the world of mathematics teaching. But our specific interest is really into the mathematics that kids are doing and our teachers that are working with us. But we're interested in what sort of mathematics people do. So I'm going to give you a brief overview of 3 things that we're quite focused on in our lab. And then, as I said, I'll go more precise into the work that we do in my research program. So the orientations that we have in our lab are, we could say, like three-pronged sort of thing. The first thing is that we work constantly in classrooms. I mean, most people do, but this is important for us. We get invited in classroom to do mathematics with the people that are there. And again, as I say, because we're in classrooms, then we might think, then we have things to say to teachers, we have implications, you should do this and that, but that's not our point of view. We're just interested in learning and studying what kids are doing in classrooms. The second aspect is, as I mentioned, our work is focused on the mathematics itself. We're interested in the sort of strategies students can come up with, the nature of the mathematics they do, and especially we're interested in this because we believe firmly that our own understanding of mathematics still needs to grow. And it's really motivating to continue understanding what mathematics can be and is for other people and for us. And I won't get into, oh yeah, so that's what I just said, but better said, I suppose, because I took the time to write it. So we start from these mathematical productions and activities to enrich understanding about mathematical productions and activities, but also about school mathematics itself. So we're strong believers that there's still a lot of things that we need to understand about school mathematics. And the third aspect is our grounding, I would say, like our epistemology. I don't need to get much into these details, and you know of these theories, most of you heard about them. But one way that it really influences us is how we conceive of mathematics. So for us, and that's our perspective, it's not an issue of arguing for it, it's just, this is how we conceive of things. Mathematics for us is an activity. It's something we do. It's something that unfolds, that happens in the midst of doing it. We're not really keen on looking at mathematics as a thing, as a static thing that is pre-decided in books that we need to, I suppose, acquire or learn of. We're mostly conceiving of mathematics as something that is moving, that always unfolds, that emerges in the midst of doing it. So that's the influence from our theories. And so our focus when we start to look at how people do mathematics, and in fact, it's how people do mathematics, that's our interest. It's not looking at it as a body of knowledge, but mostly as an activity that provokes. So our analyses that we do are about, in fact, the mathematics that people engage in, and not about if they've learned it well, if it was taught well, or things like that, which that's fine if people are interested in this, but our interest is mostly really into the mathematics that people are doing. Oh yeah, there's a small bit. So I'm from a math department because math educators back home in my university are in a math department. Whenever I say the first thing above, that mathematics is an activity, that it's dynamic, that it's open-ended, that it never ends, that there's still a lot to know, everybody nods. I'm in a math department. But when we say, oh no, we're talking about school mathematics, the things that maybe some people think is already set up, it's in the books, it's all there, then there might be differences in recollection somehow, or recognizing that movement. But for us, it's very important. Even school mathematics for us is a dynamic field, and it still needs to grow. It grows, but in the same way that pure mathematics continues to grow, or that everybody here during the 2 weeks were working on boards and stuff, making it grow. For us, it's the same thing for school mathematics. So this being said, this is the setup. This is how we educate our students. This is how the profs in our lab are working around. This is our philosophy. I wanted to talk about precisely how it gets, I suppose, a little bit more pragmatically, how it becomes research projects and the sort of data analysis and experimentations we do. So I'm going to talk to you about the research program that I'm leading since about 2011. I'm working on mental mathematics. That's my interest. It's always have been. And so I'm interested in doing mental mathematics with kids. As I mentioned, we go in classrooms. Doing mental mathematics imposes that we play around issues of time constraints. We often give quite accessible tasks to kids, but the environment is particular. And we know that. We're immersing them in a specific environment, not because it's a better environment, not because it will lead to better learning. It's just that we're really interested in these 15-second sort of constraints, no paper and pencil, no material, task mostly given orally, or sometimes written on the board or bits of it. We're interested in the sort of mathematics that people will engage in. And we know we're constraining them, but that's our idea, is to see what sort of mathematics they can create or engage with when they're under these constraints. And the mental mathematics we do, of course, we also work on some numbers, but we got quite interested right from the start into doing some mental mathematics on other topics, especially secondary level topics, because we thought we were very curious in knowing how would people engage, how would student engage on standard tasks that they normally do on paper and pencil, but then being constrained into no paper, time constraints and stuff like this. So we work on functions, on algebra. I wrote like statistics, systems of equations, trig, volume. We're currently working on percentage. We worked on area and perimeter. So we address these sorts of topics through mental mathematics. I'm going to give you examples of tasks, so maybe it offers you a better sense of what we do. So this is, for example, an example of a task we asked kids to solve for X. They had 15 seconds in 8th grade. This is another example. So we're curious in how they would solve it in that time constraint. No paper and pencil. Same thing. This was mostly for 9th graders. But we could have given it also to 8th graders, but in that case, we didn't. So this is about algebra. We also worked on functions. We gave graphs like this, and we asked, for example, students in 10th grade to add the two functions, f and g. Things like that. We could also ask it orally or writing on the board to ask these two functions. I invite you to do that one. It's very nice if you add these two functions. We also asked kids to solve systems of equations of that sort. Could be seen quite accessible. We had different sort of systems of equations also. And when we work with graph, what we often do, we don't always do that, but sometimes what we do is we give them half sheets of papers with a graph on it. They have that on their table. And they get 15 seconds to think, not using their pen. But when we say, OK, you can write down, for example, the answer on the graph, then they would pick their pen and write something to show up then after what sort of graph they came up with. Same thing with these ones, for example. When we worked on mean, for example, in statistical mean, we asked these sort of questions, like here are 4 distributions, which one have the same mean? We did ask questions like this also. Here's a distribution, very like school-like distribution that you find in textbooks. Is the mean closer to 10, 20, or 30? I just mentioned textbooks. I think it's an important thing because many tasks that we use, we just copycat them from textbooks because textbooks are filled with tasks that we could reuse, or we also use tasks that were already tried out in the research literature, but often on a paper and pencil context. So it gives us also not necessarily a means of comparison, but we get a sense of what sort of strategies students can come up with and how, when they're in a mental math context, what sort of work they would do in that as a comparison somehow. But we also, when we worked on perimeter and area, for example, we gave that sort of this hexagon on the board, and we asked them how could they transform it to enlarge the perimeter but diminish the area, or the other way around. And recently we worked on percentage, as I mentioned. So we did ask these sort of questions. Here's 3 of them. So 3 plus 50%. What's 4% of 75? Is 63% of 287 bigger or smaller than 50% of 300? So always the same context, about 15 seconds, no paper and pencil, and they try to come up with ideas. So that gives you some sort of a sample of things we do. And then I wanted to talk about the sort of results we come up with. There's slides missing, but should be something else before, but I might be. Oh, okay. No. Oh, yeah, I get it. Sorry. Sorry. I think this mixed me up. But you'll see on the right, there's always like examples of strategies that I can't talk about all of those, but you'll see some answers that kids have given up since the beginning. Yeah, it's about research questions, because what you'll see when I'll talk about the results, it's also in a 3-layer thing. So I got mixed up. Sorry for that. So the questions we ask ourselves, you might get a sense somehow, because I mentioned things, but there's 3 elements that are of quite a lot of interest for us in that research program. The first one is about strategy. So we are quite curious into the sort of strategies that kids would, and I say kids, we work with people from 6 to 66, as I mentioned. I don't know, they're all kids. But so we're interested in the sort of strategies they engage in, the meaning they give, and the mathematical meanings we're able to draw from these sorts of strategies. And I'll show you a number of those sorts. Another set of questions we also have is that we got interested in what does it mean to do mental math? I mean, is it a specific process that people engage in? Is mental math just a subset of paper and pencil, for example? Is it pre-paper and pencil? Is it something they can work on? What sort of solving processes they get in when they're doing mental math? And thirdly, we're interested, as I've been mentioning since the start, in the mathematics itself. So we're very curious into the nature of mathematics that will emerge when they're engaging in solving these sort of tasks. What can we gain from it mathematically? Maybe to think about how these topics could be approached differently, or just mathematically itself, how it's interesting mathematically. We can think about possibilities of how students are making sense of this. So we get more sensitized to how people are being able to understand this mathematics. Yeah, so those are the 3 sorts of things that are of interest for us. And I'll be specifically talking about strategies, but underneath those, you'll see we'll address these 2 elements also. So this is what I thought was missing. So let me talk a little bit about outcomes. In the work we do, because we're also interested in what does it mean to do mental math, of course, there's elements about solving processes that are more conceptual. I'm going to talk about pragmatic aspects, which are really about the strategies themselves and what they are, to give you a sense of these things. I think getting a sense of the concreteness of these strategies will be of interest. And 3 things that I'm going to talk to you about, very simple somehow: the level of success that kids have when they're solving mental math. We're still always impressed by how good they do when they're in that posture of doing mental math. I'm going to talk also about the variety of strategies. That's not a new thing, because most reports on mental mathematics will always say, and then we had 12 sort of strategies, like 15 sort of strategies. But I'm going to talk to you about this also so that you get a sense. But also through that variety, there's often some sort of alternative ways of solving, what we could call off-beaten path somehow. And they get into spheres that are maybe not standard, or they different than what we know. Maybe it's time also that I mentioned that sometimes these strategies, I've talked about success, but sometimes these strategies, they don't always work as students would like. Sometimes they get into troubles trying to try one strategy with another. And we realize that we're not that sensitized to these sort of mistakes, because by being focused on the mathematics that is being done, that it's wrong or right is not as interesting as the nature of the mathematics that is being done. So sometimes we realize that as we were sometimes reporting on strategies that kids would do, and someone would raise their hand and say, but that's wrong. Oh yeah, you're right, it's wrong, but still, have you seen that the kid is doing this and that, which has a lot of potential? So don't be surprised if you come across strategies that you wonder if they work or not. But that's part of the variety, and it's through this variety that sometimes they give us a glimpse into aspects of mathematics that we might not have think of. So it's not always in the successful strategies that we find things of interest. There's also in things that are working less, but there might be like small diamonds hidden in this. And the last thing is what we call it innovative, but mostly in that variety of strategies, there's also strategies that are quite advanced or ways of doing that we might not have think of, but are also opening up, we think, very interesting doors in terms of mathematics. Okay, so, well, there's other things about the conceptual. I'll leave it there if ever we talk about this. But one thing of interest is that all the work we do, it's very important to keep in mind that when you do mental mathematics, often the strategies that we will get are quite local. They're because of the task we gave. So if I go back, let's say, and I'll be talking about this, but if I go back, I suppose, to this task, and it has 50% of 300, the sort of strategies that students will do or engage in are sometimes quite connected to the fact that it's 300. If it would have been 289 or 500 or 1,500, the strategies would have been different most of the time. So that's why we call them very local, but also tailored. They're quite tailored to the sort of task we give. And so we see them, of course, as dynamic, as emergent, but also we recognize that the localness of those. But in that localness, there's often, as I mentioned, like diamonds or stuff that we think mathematically has a lot of work. You see, it's almost the same slide as before. That's why I got, I'm justifying myself. Okay, so I'm going to talk about these three aspects. So the success, the variety, and the innovative part. So I'll start with the aspects, the success. So one thing that became quite striking and is that students do appear, of course, there's some mistakes that happen, but they do appear to be quite successful when they have to solve our tasks. And as I mentioned, these tasks, or they're coming from textbooks, or they are already well-studied tasks in paper and pencil context. So we have strategies of students when they have to solve them in a paper and pencil context. And sometimes it's interesting to do that contrast. And what we rapidly see is that in that mental math context, the level of success and engagement is quite high. So let me give you examples. If we talk about functions, for example, and functions are very difficult. When we look at the literature on the understanding of functions from students, maybe 9th grade to 12th grade or something like around that. We don't have 12th grade in Quebec, but so working with function is very difficult. Working graphically also, they're tempted to always go back to the algebraic expressions or formalization with it. And so when we work on this, for example, I'm going to give you an example of strategies they had. So when they had to add, so the task was to add function f and g. And one of the things they pointed at, in fact, was to look at specific points that were of interest for them. So for example, in this case, if I pay attention to the crossing here, and I have to add f and g, then this is a null, like a null image, it's 0. So I know that the resulting addition will be on G. I'm not tall enough to point, but same thing here. In the case of the G function, it's 0, so the resulting point will be there. This is way too high, getting my thing out of my shorts. But so then they could add these two image lengths, this one and this one, to get at the same thing. And in this case, because there was a crossing, they would say then the image is doubled. So they would end up working with in this case, constant functions, if I'm not wrong, because they are symmetrical. Yeah, and so they would get to the added function right away. But they also did that, pointing to specific points of interest with functions like this, for example, which you might be visually tempted to draw a line just above the x-axis on the crossings, but that might be different. Same thing like that. And this one is an important one because in the function literature, we know that because we focus a lot on the fact that functions are talking about variations and variables, for reasons that as researchers, we have still a hard time to understand. The constant function is quite difficult. It creates some challenges. When we worked with them, with adding these two functions, for example, the issue that G became some sort of a translation mode, where you could, when you add F and G, F just got lowered somehow through a translation where every point being added would be lowered, giving you the parabola, but lowered in the graph. Okay, so that's an example. Same thing here, and I'll be talking about this later on. This task was a bit different, where they had to find what was added to F to give F plus G. And again here, the issue of a constant function came back in role, especially, and I'll mention it later on, but I'll mention it here, is that many students have started to talk about the parallelism of curves, which, if you're aware of that the concept, it's quite an advanced concept, still open-ended problems about this, but discussions about the parallelism of curves was a very interesting event that happened through this. Okay, so that's about success. I mean, I gave you examples of things that kids succeeded well. We might want to talk more about this, but it's important for us also to flag that there's some ease of engaging with these sorts of tasks. The second part, which might be a bigger part, is about the variety of strategies and the off-beaten tracks path sort of strategies that I meant. So they engage in a variety of strategies, but also they do differ from what we know sometimes. So in terms of variety, if I take that task that we gave, and I won't burden you with all that happened with this, but when we gave that task, we got at least 12 to 15 strategies to solve that. And kids engage with this by, for example, paying attention to extreme values, the end values, the length of the distribution, the fact that there was some symmetrical aspects in some distributions that could lead to assess the mean by it. Looking also how they could equilibrate, for example, in this case with 47, it's very special for me to be on my toes. You think you're tall, eh? I have a kid, he's that, so you think you're tall, but no. Peter, I would need you, I think. So 47 would, for example, draw the mean much farther than 42. So these differences, or maybe not paying attention also to 47 because it could be seen as way too high. So they would play with 41 and 42. So there were a lot of strategies, and I'm just giving you examples of. So they would look at near values also. I could go back. So where are the values that are quite near? And so it would mean, because it's quite near, the mean could be around this. So they would also be able to pay attention to the fact that, for example, this one is very similar to the A, but just one of difference. So then for some students, the mean would be different right away. But for others, they would say, well, it's so close that mostly it might be the mean. And if you had a 300, a data set of 300 elements, it wouldn't really matter that there's one of difference somehow. So it's quite an interesting strategy or a view of the distribution. So some look at the tendency, like where would the mean be focused in that distribution, because the numbers would seem to be around the same value. So we had many different ways of engaging with that sort of distribution. Okay, same thing. In this case, and I'll be also continuing on this later on, but in these sort of tasks, we get, again, an immense number of different ways of solving them. Students engage with them in a variety of ways. I have some examples here. So for example, some would talk about solving them as looking for the number that would satisfy the equation. Some others would be focusing on eliminating fractions, which is not surprising. Like fractions can be a burden somehow. So their first attempt was to try to eliminate these fractions and then to work on. Some have tried, like in a standard way, just to isolate the x. Some would estimate how much it would be. For example, in the top one, if 2/5 of x needs to be equal to half, 2/5 is less than a half. So what does it need to have in order to become a half? So those would be the sort of reasoning that some students would have. Creating an equivalent equation also, depending on which task they were given, was something they would do. Factorizing, undoing what's been going on. I have 3 times a number that gives me 3/4. Then I have, in fact, 3/4. So x becomes a quarter. Reading upside down, well, that's a tricky one. Some didn't like the fact that x was on the denominator, I would say. So they, in their language, they flipped it in order to solve x over x equals 5/3. So I'll open a parenthesis. This raises a very nice question of, are they equivalent equations? I'll leave that to you. It's a very interesting thing, I think. Some use ratio. So we had an immense number of strategies that came out of this. And one main element, and especially the teachers that had invited us, they were quite struck by this, is that, well, I'm giving you 12 here, but one reaction from the teachers was, okay, solving an equation is more than isolating x. That's quite clear when we see all these ways of doing that end up to the same sort of answers. Okay, and then, yeah, time is good, I think we're okay. I wanted to talk about different sort of strategy. It comes from what I've mentioned before, but also ways of engaging where I think it's quite exciting, the sort of mathematics that has been done with the students. So when we talk about, so I mentioned that distribution, and there's one strategy that I didn't talk about, which was very exciting. It's discarding the 400, so the 40. So we had students who mentioned that in order to assess these distribution, what they had to do, in fact, they could just not pay attention to the 40s and then have a distribution that is 1, 2, 4, 5. The second one, 1, 2, 3, 4, 5. The third one, 1, 2, 7. And the fourth one, 0, 2, 4, 5. And they were able to compute through this because it was much more accessible. So that strategy is quite interesting, but it's particularly interesting because it raises issues about how that distribution has the same properties as a distribution with 40 less. And somehow, well, that's some sort of a bell curve, but that's not, and it's continuous, whereas those are discrete. But it's the idea that the property of the distribution, in fact, can be just translated. So there's a family of distributions that have the exact same properties, which is something we learn in first year, at least at home, first year statistics course with the operations you can do on some distributions. Coming from 9th graders was quite interesting. And in particular, we might think that taking out 40 is the only options, but you could add 100, you could subtract 35. And while we talk about, sorry for people who I just coughed. One thing that we thought of interest also is to start raising questions about the sort of operations we could do. What if we doubled, for example, times 20? What if we would add distributions together? What would happen to the properties, to the standard deviations and stuff like this? So on our side, when we say there's things that are innovative, it's also things that lead us to do more mathematics on our side and to explore elements that might not have that we might not have explored before. But also it leads us, especially because we're in a math department, we got with colleagues that are statisticians to see what are the options. What happens when you, let's say, double the second one and you add it to the third one and you subtract the first distribution? What goes on, in fact, to the properties of these distributions? Do we keep the standard deviations? Do we keep the mean? Does the median stays the same? So those are questions also that it led us to talk about. That's an example. I mentioned the parallelism of curves. So that was something also that we thought was quite innovative, to reflect on constant additions to one function, but in terms of the parallelism. Okay, and the one about the algebraic equations, which we thought was also quite interesting, especially because it made us think about what does it mean to solve an equation. So that example is a nice one of this. So the first thing, when they got the 2/5 x equals a half, some students' reaction when I mentioned that they wanted to eliminate fractions was to double the equation, which would give them 4/5 of x equals 1. This might seem simple as an action, but one thing that we came to realize is that when you solve on paper and pencil, most of the time we attack whatever's linked to the x. So the 2/5, you divide by 2/5, for example. In this case, doubling the half, so attacking a number in the equation, was something quite surprising for us. It makes a lot of sense, but it's also, as I mentioned, quite linked to the expression that is there, to the equation. But attacking the half is something that we haven't seen on paper and pencil work. So that's already something. But what's a step more, some students who have doubled the half ended up with this. So there are many ways then to address how to solve for x in this case. You could, I suppose, divide by 4/5. You could do different things. And so one student in particular, when she ended up here, mentioned, oh, the answer is 5/4. Okay, how did you do that? She said, I just read. This is 5/4. And so someone in the classroom say, oh, because you divided by 5, or you multiplied by 5/4. She said, no, I didn't multiply anything. Reading this is telling me it is 5/4. In the same way that if I tell you x plus 2 equals 4, you might not subtract on each side minus 2. You know it's 2. Or if I say x plus 1 equals 2, you know right away that x is 1. You could do minus 1 on both sides, or in this case, adding. Yeah, x plus 1 equals 2. Yeah, that's right. It gives 1. Going too fast. But what's quite striking is how this could be seen as, in fact, the end equation. Like this gives me the answer right away. And so not necessarily having to make divisions, or dividing by 4/5 or multiplying by 5/4 in order to get the x. Just being able to read it right away. In the same way that, as I mentioned, you could read x plus 2 equals 4 as knowing right away that it's 2. And it led us also, by probing into some literature, there's even some people who would argue that when I give you x equals 2, you still have to read that equation in order to say that x equals 2, because x equals 2 is an equation in its own self. Yeah, so those are examples of. I think it gives us some sort of an outline of. And maybe one question I'd like to rapidly address is then what's next? So once we've been doing that sort of work for a number of years, 14 somehow, we're not in our 15th anniversary of doing this, but so what's next? So one thing we were aiming at looking, in fact, is once we know all of this high level of success, this sort of variety of strategies, and new ideas that we can gain from those in terms of mathematics, what's next? So the new orientations we have is motivated by that. We thought we would address topics in high school that are quite difficult, that we know from the literature, that we know from experiences with teachers, that are problematic or troublesome for students. And we're quite interested, in fact, in knowing what if we address these topics that are creating issues big challenges? What if we also address them through mental math? Could we gain some insights that it could be about what these topics are, what are the sort of reasoning kids are engaging with, the sort of mathematics they would do. So this is where we're at. So we're curious on the potential of mental mathematics on difficult topics, and what this context could provoke somehow. Could it provoke or enlarge some ways of doing with these concepts that are problematic, but we might not have all the keys itself and some sort of reasoning that students would. And so it could, as I mentioned, like to inform us, to better understand, to trigger reflections, to inspire ideas, like all these things, but about these difficult topics. But it also obviously might trigger some reflections on mathematics itself and how we could address them also and approach them with students. That's it for me. I was fast.